Last time we saw how to calculate some basic limits using algebraic methods, and today we're going to expand on that with some more limit rules. We saw previously that when we have a polynomial p of x, to evaluate the limits at x equals c, instead of using the sum rule, the product rule, the constant multiple rule, all we really needed to do was plug in x equals c into the polynomial function. So in other words, when p is a polynomial, the limit as x approaches c of p of x is the same as the function value p of c. This property is also true for other functions, such as rational functions, trigonometric functions, and exponential and logarithmic functions, with the added condition that the c that we're evaluating in has to be in the domain of my function. So as long as c is in the domain of my functions, to evaluate these limits, all I really have to do is evaluate the point in that function. So if r is a rational function, the limit as x approaches c of r of x is the same as r of c, or the same if we have a trigonometric function or an exponential function or logarithmic function, then to take the limit of that function, we just have to plug in the value x equals c into the function. So let's look at this example. I want to find the limit as x approaches 0 of 5 plus the log base 2 of x plus 1 over 3 cosine of x times 2x cubed plus 4x plus 1 over x plus 3. First, we need to see if x equals 0 is in the domain of these various functions. So for the log base 2 of x plus 1, logarithms have a domain of x is greater than 0, but since I'm adding 1 into this function, then we're okay to do the limit as x approaches 0. For the cosine, the domain of cosine is all real numbers, but I do need to watch to make sure that I'm not dividing by 0 here. But the cosine of 0 is 1, so we're okay. For the rational function in the second set of parentheses, the domain will be all real numbers except x equals -3, because that's where the denominator is going to be equal to 0. So in all of these, I can plug in x equals 0 into the various functions. So to evaluate this limit, that is all I'm going to do. I'm going to plug in x equals 0. So this limit is equal to 5 plus the log base 2 of 0 plus 1 over 3 cosine of 0, and all of that times 2 times 0 cubed plus 4 times 0 plus 1 over 0 plus 3. Now we just need to simplify. So the log base 2 of 1 is the same as saying 2 to what power gives you 1, which is 0. The cosine of 0 is 1, and now we can simplify the rest of this. So 5 plus 0 is 5. 3 times 1 is 3. 2 times 0 plus 4 times 0 plus 1 is 1 over 3. And 5/3 times 1/3 is 5 over 9. So that's my final answer. Again, the idea here is that for polynomials, rational functions, trigonometric, exponential, and logarithmic functions, as long as c is in the domain of this function, and that's where I'm taking the limit at, then to take the limit as x approaches c, I just plug in the value x equals c into the function itself. The next rule that we're going to look at is the cancellation theorem, but before we get into the theorem itself, I want to show why it's needed. So if we look at the first example, the limit as x approaches 2 of x squared minus x minus 2 over x minus 2, we might see that this is a rational function and try to use the quotient rule to evaluate this limit. But if we do that, then we'll end up with 0 in the denominator. And so that doesn't necessarily mean that this limit doesn't exist, it just means I can't use the quotient rule. Or the rule that we just talked about with rational functions, I can't use that one because 2 is not in the domain of this rational function. So I need some other rules to deal with things like this. So the cancellation theorem says if I have another function g of x such that g and x are equal to each other near x equals c, but maybe not at c itself, then I can say that the limit as x approaches c of f of x is the same as the limit as x approaches c of g of x. So the idea is if I have two functions that are equal everywhere near x equals c, but maybe not at x equals c itself, instead of evaluating the limit of f of x, I can instead evaluate the limit of g of x, which is probably an easier function to work with. So with the first example, we might notice that we can factor the numerator into x minus 2 over x plus 1 over x minus 2, so that we can cancel the x minus 2 in the numerator and denominator. Hence the name of this theorem being the cancellation theorem, where all we'd be left with is x plus 1. Now, as functions, these two are not equal to each other. X squared minus x minus 2 over x minus 2 has a whole at x equals 2. That x equals 2 is not in its domain. But x plus 1 is a polynomial, so its domain is all real numbers. So these functions aren't equal to each other, but they're equal to each other everywhere that x doesn't equal 2. So they're equal everywhere near x equals 2, but not at x equals 2 itself. So I can use the cancellation theorem to say that the limit as x approaches 2 of x squared minus x minus 2 over x minus 2 is equal to the limit as x approaches 2 of just the quantity x plus 1. And since now we just have a polynomial to evaluate this limit, I just plug in x equals 2, so we get 2 plus 1 equal to 3. For the second example, I'm looking at the limit as h approaches 0 of the quantity 1 over 2 plus h minus 1/2 all over h. Again, I have the problem that if I try to use the quotient rule, I'm going to end up with h equals 0 in the denominator. And you'll see this come up a lot in calculus. And so you want to find some algebraic way to end up canceling out that 0 in the denominator so you can evaluate this limit. So here, since I have a fraction in the numerator, or two fractions subtracted to each other, I'm first going to find a common denominator by cross-multiplying. So we're going to get that the limit as h approaches 0, cross-multiply 1 times 2 is 2, minus 2 plus h times 1 is 2 plus h. All of that's going to be over 2 times 2 plus h, all over h. And I'm going to go ahead and put this over 1, so that now I can, to divide fractions, I'm going to multiply by the reciprocal. So this will be equal to the limit as h approaches 0. 2 minus 2 plus h, if I distribute that 2, I'm going to have 2 minus 2, which is 0, and then minus h over 2 times 2 plus h. And then, as I said, we're going to multiply by the reciprocal, so I'm going to multiply by 1 over h. Now I can cancel the h's, and I'm left with the limit as h approaches 0 of negative 1 over 2 times 2 plus h. And now I can use the quotient rule because I no longer have a 0 in the denominator. So to evaluate this limit, I just plug in h equals 0. So we're going to have negative 1 over 2 times 2 plus 0. 2 times 2 is 4, so we end up with negative 1/4 for our final answer. The last theorem that we're going to look at today is called the squeeze theorem, or the sandwich theorem, and it states if I have a function f of x that I'm wanting to find the limit of, and I can find functions L and U such that L of x is less than or equal to f of x is less than or equal to u of x for all x near my value of c, not necessarily at x equals c itself. Furthermore, if I can find that the limit as x approaches c of L of x and the limit as x approaches c of u of x exist and are equal to each other, then I can also say that the limit of f of x equals that same L, because it's kind of sandwiched between these two other functions. So the idea here is that if my function f of x is more difficult to find the limit at, if I can find two functions that are below and above it that are easier to find the limit at, then I can use those to find the limit of my harder function f of x. For example here, I have f of x that I don't know the exact formula for, but I want to find the limit as x approaches 0 of f of x. But what I did do was I was able to find two functions, one minus the absolute value of x and one plus the absolute value of x, that near x equals 0 satisfy that inequality, that 1 minus the absolute value of x is less than or equal to f of x is less than or equal to 1 plus the absolute value of x. Now note that over here the inequality would have to switch, but since I'm looking at x equals 0, my inequality only has to be satisfied for x is near 0. So I can use the squeeze theorem to help me find the limit as x approaches 0 of f of x. To do this, I'm going to take the limit as x approaches 0 of the functions above and below f of x. So if I look at the limit as x approaches 0 of 1 minus the absolute value of x, that's just going to be equal to 1 minus the absolute value of 0, which is 1. And then on the other side, we have the limit as x approaches 0 of 1 plus the absolute value of x, which equals 1 plus the absolute value of 0, which also equals 1. So since I got the same value here for the limit as x approaches 0 of the lower function and the upper function, then by the squeeze theorem, I can state that the limit as x approaches 0 of f of x also equals 1. So this ends the different rules and theorems that we have to calculate limits using algebraic methods.